About our sponsor, SNIA. They're sponsoring this webinar, and SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,500 active contributing members, and 50,000 participating IT end users and technologists worldwide. The Storage Management Initiative, or SMI in SNIA, was created to develop and standardize interoperable storage management technologies and promote them to the storage, networking, and end user community. So that is SNIA. Now some logistics for today. You can ask questions during the presentation by selecting the Ask Question option and entering your questions. And these slides are going to be available as an attachment, or at the attachment tab at the bottom of your screen. Okay, so moving right along to the legal stuff. So before we get started, take a look at the SNIA legal notice on this slide. It provides SNIA's copyright notice regarding the use of the material we are going to present. SNIA is not providing any legal advice, and there are no warranties expressed or implied. So if you want to reference this material, please do it at your own risk. Now let's get on to the presentations. Our first presenter, Rochelle, is a storage technology enablement architect at Intel. Say that 5 times fast. She started her career as a developer and is now, as you can see on the second paragraph here, involved with almost every standards body there is.
There's a couple I don't work with, just a couple.
What, like 2? Her co-presenter, Curtis Ballard, is a distinguished technologist with Hewlett-Packard Enterprise, HPE, the storage organization. And like Rochelle, he also started as a developer and then moved on to the world of standards bodies. The good thing about them starting as developers is they can answer almost any question that you guys can come up with. So we're going to start off with Rochelle and then Curtis, and after that, we'll have the QA session. Rochelle, do you want to take it away?
Thanks, Rob. Okay, so what we're going to talk about today is really about NVMe and NVMe-oF and manageability. So what we're going to start with is an overview of what the manageability models look like for that, and then I'll hand it over to my esteemed colleague, Curtis, to talk a little bit about some of the more detailed applications of that, and then how we simplify that. So that's kind of our overview for today. So what we'll talk about here first is going into some of the Swordfish models and how we've modeled NVMe and NVMe over fabrics using Redfish and Swordfish. So I'm not going to do a real detailed primer here of Redfish and Swordfish, but what we are going to do is talk about how some of these basic models map between the Redfish and Swordfish model and NVMe. So what you can see in this slide is a comparison between the left and the right sides. On the left is the Redfish and Swordfish models, and on the right is the equivalent models in NVMe. So in the Redfish and Swordfish models, we have a rough hierarchy here that we use for traditional storage as well as for NVMe storage. We use exactly the same models. We just apply them slightly differently for NVMe and NVMe over fabrics. On the NVMe side, you see the NVMe objects that you've grown to know and love, or grown to know and hate, regardless.
No love.
Depending on your perspective. But you have, your NVMe objects, you have subsystems, you have IO controllers, admin controllers, discovery controllers, all sorts of your favorite controllers. You have namespaces, you have endurance groups, you have sets. And as you can see on the left here, these map into our traditional objects that we use. So we have our storage object, which maps to our subsystem. We have controllers, which in traditional storage, those are physical controllers, we reuse those to be the logical controllers in the NVMe space. So you can see the same hierarchy, same structure actually works really well. So you'll see these names propagate throughout. And then we use the storage pool concept that maps nicely to endurance groups and sets. And then below those storage pools where you would have volumes, that maps nicely also to that namespace concept. So you can see that same hierarchy, and you'll see that throughout as we work through. So that basic NVMe model is the same hierarchy that we use for overall subsystems. And that we use for block and file, or for block structures, and for NVMe. That's not a very complete model when we start talking about NVMe over Fabric, so we'll start expanding out on that. So here's an example of using NVMe for a drive, because what I just described isn't a complete model even for, say, a basic drive. There's other things you need to have there. So in Redfish hierarchy, we have /Redfish/v1/storage, where we put that subsystem that I just talked about. And under that, you would have links to an instance of that, and then links to your volumes, aka your namespace underneath that. You have links to your storage pools, which would be your endurance groups and sets if those existed, and the relationships to the namespace underneath that. And then you also have links to your controllers, where you would have, depending on the complexity of your device, your I/O controllers, your admin controllers, and then potentially your discovery controllers as well. And then on the second blue object line down there, we have where we would represent our physical attributes of the system. So anything that's instantiated would have some physical attributes, and that we put those in /chassis. So that's where, in this case, we're showing a representation of a drive. We would have a drive object, and that is where we basically encapsulate all the stuff that's outside the purview of NVMe itself, but we have to model all of those physical elements. So LEDs, blinky lights, any of those physical attributes of the system, the thermals, power capability, that kind of thing. And then there's just some other normal attributes of the management entities, the registries, accounts, sessions, all those kinds of things are also represented here. Moving on a little bit, there's a lot of pieces still missing from that to model the whole system. So we have a couple of additional pieces here. In green, we have the basic network connectivity that you're going to plug in. So this is where you get a network adapter, and that's going to have exactly the same pieces you would have for network adapters attached anywhere in a system. So you would have your network device functions and your network ports. And then we have two different things that we model under fabrics. We model, and this is the same fabric modeling that we use, not just for NVMe over fabrics, but for CXL, for Ethernet, and this is just general Redfish, Swordfish utilization of fabric. They all use the same fabric model. We have two different things we're going to talk about here, one of which is modeling our access rights, and the other one is modeling connectivity. So connectivity is really your standard fabric utilization, and access rights is really more very storage centric. How do we model who gets what the device says, who gets to see, who has permissions to access me? It's really the simplistic way to look at that. So looking at those, we have two different views here. One shows each way. So the extended connectivity, that's exactly how you'd expect to see this mapping of switches, endpoints, and zones. The same zone concept you're familiar with from Ethernet or from Fiber Channel. It's exactly that same abstracted model here. And then we move on to that access management. And here we use this under fabrics because those endpoint contracts are very, very useful. And then we model that access connectivity in the form of connections. And so that connection would have, say, a volume represented in their namespace that says who has read and write access to me, and then it shows that list of related endpoints. It says here's the list of endpoints, aka initiators, that are allowed to access and have read and write type permissions associated with those endpoints. And all of that maps back to that information that's provided from those NVMe devices or from any type of standardized storage device. Looking at those standardized models there, let's look at a really complex NVMe over Fabrics concept. And by when I say, well, we will look at it, I mean Curtis will look at it. And let's look at how we model that in Swordfish, though, because we could make some of these NVMe-oF concepts really, really complicated and expose that up. But our goal here really isn't to do that. What we really want to do is simplify these things as much as possible and make sure that our clients and end users have as simple a presentation as possible. So Curtis will take it from here and talk you through one of these concepts.
Thanks, Rochelle. So I'm going to talk with you a little bit today about one of the more interesting and complex aspects of NVMe over Fabrics, as Rochelle indicated, specifically storage device discovery. Storage device discovery for NVMe over Fabrics when you're connected to an Ethernet fabric is different than some of our traditional storage devices where, for example, you plug a SSD onto a SAS interface and you have physical detection. The device immediately shows up in your operating system. When you have an NVMe-oF device attached to a Ethernet fabric, it's a device out there in the fabric that you can connect to, but you need some information about how to connect to that. The NVMe over Fabric model for how you discover those devices is called Discovery, and we use special NVMe over Fabric's NVM subsystems that use a thing called discovery controllers. When you connect to a normal NVMe subsystem, you use I/O controllers for doing your operations like reading and writing. For finding things in your fabric, you can connect to a NVMe over Fabric's discovery subsystem, which contains discovery controllers. And there are two types of discovery controllers discussed in the NVM Express specifications, a direct discovery controller and a centralized discovery controller. So we'll cover those in 2 slides here. To give you a brief introduction to a discovery controller, in this slide we've got an example NVMe storage system. This may be a software-defined storage system spread over a number of compute nodes. This may be something like a storage array that is presenting NVMe storage. And in this example, we've got a NVMe storage system that is presenting 6 different NVMe over Fabric subsystems. You can think of that as kind of like 6 different logical SSDs are being presented by this NVMe storage system. And then we have a discovery subsystem that is the entity that you can connect to find out about those other systems. Splitting that out, your discovery subsystem contains a discovery log page, which has entries in it that describe the different subsystems that it is telling you about. And there's a couple of special types of discovery log page entries, but we're most interested in the ones that describe subsystems. So in this example, discovery log page, there's 6 entries here describing the different NVM subsystems. And breaking that down even a step further, we take a look at one of those example discovery log entries, and it gives you quite a number of pieces of information here about that NVMe over Fabric subsystem. Most of that information is necessary information to set up your connection for using the device or for creating the connection for using the device. Things like transport type, address family, tells you that you're talking to an Ethernet device, what types of Ethernet addresses, are there specific transport requirements that you have to use for connecting, et cetera, et cetera. So here's the information you need to connect to that single NVM subsystem. That gets even more interesting as your system grows and you have a set of NVM subsystems. Then we get to what we call a centralized discovery controller. Each one of these boxes down here on the bottom is an NVMe storage system. Like the previous example, might have 6, might have 12, might have 10,000 NVM subsystems in any one of these. Connecting to and discovering all of them individually can be a time-consuming and complex process. So NVM Express defines a mechanism called a centralized discovery controller. That's a specialized NVM subsystem that contains a discovery controller, which aggregates information from a set of NVMe storage systems into a single spot, allowing that to be reported out to the network. So a host can have a little bit of information for how to find a centralized discovery controller, or NVM Express defines some automatic discovery of discovery controllers mechanisms, and the host finds that this centralized discovery controller, it can discover all of the systems that are available to it. As you can imagine from that whirlwind overview, there's a lot of different pieces of information all aggregated together and copied up through your connection up into the host to establish your connections. As we're working on figuring out how to map these things using the Swordfish model, we took advantage of the NVMe model and the way that these systems are built up as controllers, and we created what you see here in this diagram, where your storage object has 3 different NVMe subsystems in it, NVMe 1, 2, and 3 in this example. And NVMe 1, its controllers, just has the discovery controller, the entity we've talked about for discovering your devices. That might be a centralized discovery controller. It might be a direct discovery controller. The host doesn't have to care. The format of the information it gets back is the same. That discovery controller contains essentially pointers that go over to the other NVMe devices. In the Redfish model, we decided to copy that model even more literally and create actually pointers from the discovery controller in the discovery subsystem that point directly into the NVMe subsystems. And by nature of the mechanism we have available with Redfish and Swordfish, we're able to also have each of these NVMe storage subsystems able to report back to the discovery controller. So we ended up creating a extremely simple model for finding all of the different subsystems from the discovery controller. We've got an example here in the next slide that shows you a mock-up of subsystem in Swordfish. Here we go. So this is your Redfish v1 storage NVMe over Fabric subsystem 1. And inside that subsystem, this is a storage subsystem, and it contains a link that points to an NVMe over Fabric discovery subsystem. One link, one pointer goes over to Redfish v1 storage NVMe-oF discovery. Follow that link, it will take you over to your discovery controller. We have a mock-up of that in our next slide here. Here's your discovery controller. Your discovery controller has a few properties, and then it's got a discovery subsystems list. And inside that discovery subsystems list, we've got links that go to Redfish v1 storage NVMe-oF SS1, exactly where we were a second ago. In this example, there's also NVMe-oF SS2, and those are super simple links that take you directly over to the subsystems. So you might ask, what about all the parameters that you just showed me in the discovery controller? The discovery controller had these tables of all sorts of information. This example just has a link. Well, the magic of being able to use Swordfish is that this link takes you straight into the management interface of the subsystem that you want to connect to. And that subsystem has all of the connection properties, all of the properties that you need to make a connection, plus a whole lot of additional properties. We don't need to copy those. You can use Swordfish to significantly simplify some of your discovery mechanisms for your NVMe over Fabric devices. And so this is an example of how Swordfish maps the functionality into simplified and usable manners without copying absolutely everything from NVMe over Fabrics. And there's other examples. We only have time for the one today. So Rob, that takes us back to Q&A.
Great, Curtis, thanks a lot. So one question from Rick at Park Place Technologies. On slide 11, he says, is this true for Rocky and iWarp and NVMe over TCP? And I'm guessing he means the transport layers.
Okay. So I just said Ethernet. So I think the example is, do you use the same discovery mechanism for all the different types of Ethernet that's supported by NVMe over Fabric? And the answer to that is yes. All of the different types of Ethernet use the NVMe over Fabric device discovery with discovery controllers. And if we really wanted to dig into it, there's all sorts of variations where in some environments, if you're hooked up to a RDMA Ethernet fabric, your discovery controller is a RDMA discovery controller. Some people have implemented that their discovery controllers are always on TCP/IP, and you can have a discovery controller on TCP/IP that tells you that you have to go connect over to a RDMA fabric to get to a subsystem. So there's a lot of flexibility in how the discovery controllers describe the different NVMe over Fabric subsystems that you can connect.
Great, thanks. So we have Redfish, we have Swordfish. Both have been mentioned quite a bit. Rochelle, can you explain how where they both sort of fit into the whole process? You're muted, I think, Rochelle.
I was double muted. I was going to make sure nobody heard me. So thanks, Rob. Yeah, so Swordfish is an extension of Redfish. So one of the things you saw in there, and we highlighted even in the mock-ups, was this is all in /Redfish/v1/ / whatever. Swordfish is not an independent thing. Swordfish is the storage components in Redfish. So Redfish defines protocols. It defines base models, like the fabric portions, those are all Redfish. When Swordfish is defined by SNIA and to cover the storage models. NVMe and NVMe over Fabrics work is done as a joint NVMe and NVMe over Fabrics modeling within Redfish and Swordfish is done. Not NVMe and NVMe over Fabrics work. The work for the representation is all done in SNIA as a joint alliance agreement work between DMTF and SNIA. We throw appropriate schema work back to DMTF, but we basically develop it as the core expertise within SNIA. So it's a joint collaboration between DMTF and SNIA, where the primary experts to develop the work are in SNIA. So we do the documentation, we do the core schema work, we do the mock-ups, we do conformance test work, we do interoperability labs, and we partner very closely with DMTF, but we don't develop it's not a separate separate set of schema independently. It's basically a pure extension. And it was a really long way to say it's a pure extension, but folks get very confused about thinking it's something different. And a lot of times DMTF are actually starting to point to Swordfish because it's very much a if you want to do NVMe and NVMe over Fabrics work, it's Redfish plus Swordfish to get there.
Great, thanks, Rochelle. Here's one I think again for you, Curtis, from Aubrey. Hopefully I pronounced that right. Is the centralized discovery controller also responsible for load balancing and deciding how to distribute data across NVMe over Fabric storage solutions?
Thanks, Rob. So that's an interesting question. I almost started to say no. And generally, the discovery controller isn't responsible for the load balancing, and certainly isn't responsible for deciding how to distribute data across an NVMe-oF storage system. The discovery controller does have some additional things, though, like zoning capabilities, and there are some things that you can do behind the scenes to only describe certain paths to subsystems, to do a little bit of path steering with the discovery controller if you really want to get into how things are described using the discovery controller. But certainly how the data is distributed across an NVMe storage solution is usually storage solution specific, almost always storage solution specific, and load balancing across the paths usually is also done in a layer other than the discovery controller.
Great. Here's another one for you, Rochelle. Is there some open source code that one could look at to kind of get themselves up to speed on the things we've talked about here?
There are several different sources for looking at, and some new things coming out shortly. In fact, at Supercompute next week, be a good time to stop by booth 1403, the Open Standards Pavilion, and talk to some of us about this. In Swordfish, we have some mock-ups at swordfishmockups.com that will show these configurations. We also are developing some open source emulators that work with this. We're also partnering with two different efforts. First, in the Open Fabrics Alliance, they're working on a project called Sunfish, which is a reference implementation for fabric management. And so when we're looking at managing NVMe over fabrics and CXL fabrics and the like, a lot of the fabric management pieces that we're talking about here will be represented in that Sunfish infrastructure. Another related area for NVMe is also the NVMe over fabrics boot. So that's adjacent, not orthogonal, it's an adjacent area. And so that's another area that actually Rob, Curtis, and I are also working on. And there's some open source reference or some open source code that's coming out of the in conjunction with the boot spec that's being developed in NVMe, that's getting pushed up into the Linux, multiple different work streams in Linux, everything from EDK2 to SPDK, and some manageability pieces as well. So there's a lot of different elements that are working around this that we touch on. If folks have some interest in this, please feel free to reach out to me, and we could talk more about all the different pieces around this.
Great. And I'm going to flip to the next slide because someone's asking where they can get some more information. And here's a whole lot of information if you want to delve in. And I think we maybe have time, if we're quick, 1 minute left for the question here from Celestica. Probably, Curtis, how is centralized discovery controller implemented today? Is it a separate system or a function within a fabric switch or part of a storage target system? Okay,
this is one of those great questions where you get an answer, yes. The centralized discovery controller in the NVM Express specifications does not have a definition for exactly where you have to implement it. It's a service that's implemented in the fabric. The specification creates some ways to discover if there's already a service in the fabric. So you could have it implemented multiple places, and when a new discovery a new device powers up that's capable of running a centralized discovery controller, it could discover there was already one and not operate. Some of the most common implementations are going to be things like implementing it with a fabric switch or part of a storage system, as was asked in the question. Those are two of the most likely places they'll be implemented. I know of one implementation is switch today, one implementation that runs in a container that you can deploy anywhere in your fabric.
Great. I think that's all we have time for. Thanks everybody for listening. And as Rochelle said, if you're going to Supercomputer, there's lots of information on all of this at the booth there. All right.